Swayam Prabha. Digital India. Educated India.
So, in the context of MD simulations, our initial motivations to study statistical mechanics is to relate microscopic data of the system and relate these microscopic data to macroscopic observable or experimentally measured properties. So, in this context, we have looked at various kinds of ensembles with which the mechanical state of the system can be described via microcanonical, canonical, Gibbs and Grant canonical ensembles. And by looking at all these ensembles, we also found how the microstates are distributed in phase space. And we also looked at various concepts such as trajectories, ensemble average, time average, and relationship between classical thermodynamics and statistical mechanics. So, in this lecture, we will take all this forward and try to relate the microscopic data to macroscopic measurements. So, first the question comes, when we try to measure some property in an MD simulation, whether it depends on a particular ensemble with which the system is studied. So, this is a question of what is the equivalence of ensemble averages of any property. So, it turns out that the conclusion is that as long as the system size is large enough, the property that you measure should be independent of which ensemble you measure from. However, when the system size becomes smaller and smaller, then you see a difference between the measured properties between two ensembles. So, in order to prove this, we take two ensembles, microcanonical ensemble and then canonical ensemble. As you note, microcanonical ensemble is fixed N, V and E, and canonical ensemble is with fixed N, V and T. Once we identify the ensemble, we know what is the thermodynamic potential related to the partition function. In the case of microcanonical, the entropy is related to the partition function. In the canonical framework, the Helmholtz free energy is related to the partition function. So, now let us say in the microcanonical ensemble, since we fix the volume, pressure is allowed to fluctuate, and we may be interested to measure the average pressure of the system. So, this average pressure is written here with a bracket here. This angular bracket basically means it is an ensemble average. We also keep in mind that the averages could be either ensemble average or time averages. So, for this particular proof, we are taking ensemble averages. We also remember that ensemble averages and time averages are equivalent provided the system is ergodic. So, with that in mind, we write the average pressure of the system is you measure the instantaneous pressure at a given microstate, weight the microstate with respect to the distribution function, and then you integrate over all possible microstates. So, that is a definition of average pressure in the ensemble average framework. And this expression should be something familiar to you, because if you know any probability function p of x for a random variable capital X, we know that the mean value of this capital X is given by the first moment of the probability function. Okay. So, you can see this expression is basically analogous. Only difference is here we are talking about a one dimensional integration, whereas here we are talking about a 6n dimensional integration. I am writing in a simpler form, eliminating all the dp, dr and the prefactors, so that the notation is little condensed. But you have to remember that this integration is over 6n dimensional space. So, now once we know that microcanonical ensemble, we also know what is the functional form of the microstate distribution function, which is the Dirac delta function divided by the partition function. And this direct delta function is non-zero only in certain microstates where the total Hamiltonian is equal to the energy that is being fixed in the ensemble. So, we will keep this as an expression for getting average pressure, ensemble average pressure in a microcanonical ensemble. So, now we will go to canonical ensemble. Here again we write ensemble average of pressure in a NVT ensemble. So, here the expression is same, only difference we have to make here is the distribution function rho should depend on the ensemble variables which are NV and T, and we substitute the expression for rho as exponential of minus beta Hamiltonian divided by the partition function. So, now if you look at this expression, this is the integration over all the phase space, 6 n dimensional phase space, and we are constraining the temperature in the system. So, each microstate is allowed to fluctuate this energy. So, energy fluctuation is possible. However, when you take a very large system size, you will find that the energy of the system hovers around a mean energy of E bar. Around that there will be little bit of fluctuation. By making this system larger and larger, you will see that system is found in an average energy state of E bar. So, then with this particular approximation, we can rewrite this expression with an approximation that the average energy of the microstate is E. So, I substitute for Hamiltonian as E bar and I take that out of the integral, because we are talking about a microstate where the energy is around the mean energy. So, then this integral over this phase space can be over only those regions in which this Hamiltonian is equal to this average energy E bar. Okay. So, if you want to put, you can put E bar here. So, that you can see how we are approximating this integration over all the microstates with all possible energies into a small region where the energy is equal to the average energy, and this is possible only because we are talking about a system of very large size. So, now we have to work with the partition function for the canonical ensemble. So, in order to do that, we take the help of thermodynamics. We look at the expression relating the Helmholtz free energy to entropy via this expression. Helmholtz free energy is equal to total energy minus temperature times the entropy. So, this is the definition for Helmholtz free energy in classical thermodynamics. So, now I am going to multiply by beta on the left hand side and right hand side, and we have to remember this beta is 1 by kBT, where kB is a Boltzmann constant, capital T is a temperature. So, by writing that, I am able to replace this beta times A using the partition function expression from here, and beta E remains as such. This minus S by kB is obtained from the relationship in the microcanonical framework, which is minus S by kB is equal to minus ln q NVE. So, that I am substituting here. So, now if you rewrite this, you will be able to show that the canonical partition function q NVT is equal to exponential of minus beta E times the partition function for microcanonical ensemble. So, this is a relationship that we are able to write for a classical thermodynamical system, in the sense the system is very large and the energy is about a mean energy of E. Even though in the QNVT the energies are allowed to fluctuate, here we are taking a mean energy value for a very large system. Suppose if the system size is not infinitely large and if it is finite, this expression should have been something like this. You sum over all energies E. So, this should have been the actual expression, but now we are not allowing a large variation in energy, we are talking about one single average energy. So, there is only one component in the summation, and that is what this is. So, now we take this relationship between the partition function of NVT ensemble and the partition function of microcanonical ensemble and substitute it here. and you see that these two terms cancels, and then you are left with the remaining term, which is integral of P times delta times d gamma by q NVE, and this expression and this expressions are essentially the same, meaning we are able to show the average pressure measured in the canonical ensample and the average pressure measured in the microcanonical ensample are the same. But this condition is satisfied only under two situations. One is the system size is large, so we are able to make this approximation, and second, the temperature in this NVT ensemble should give you a energy E that was fixed in NVE ensemble. So, this E here, so the temperature that is fixed in canonical ensemble should yield an energy which is fixed in the microcanonical ensemble. So, provided these conditions are satisfied, then one can show that the average property measured in either of this ensemble should be similar. So, the conclusion is, in the thermodynamic limit, the averages are independent of the ensemble. Even though I have showed this here for pressure, you can actually write a general expression relating any property between two ensembles and relate their relationship. And if you do this analysis, you will also find that the difference between these measurements, let us say pressure measured in NV ensemble and pressure measured in NVT, this should have been NVT, and the difference goes as 1 by n, where n is the system size. As n goes to very large value, you see the difference goes to 0, whereas for finite n values, there will be a significant difference between these two measurements. Now, we will talk about some other simple thermodynamic averages such as temperature, pressure, etc. So, in order to do that, we first recall that the Hamiltonian of the system is written into two parts of kinetic energy and potential energy, and we have already noted the definition of kinetic energy using the momenta of the particle, where here the sum from I is equal to 1 to n is over the number of particles. This alpha here is for x, y and z coordinates, and pi square alpha by 2 mi, and then summed over all these components will give you the total kinetic energy. And similarly, the potential energy is written into two parts, one that is the external intermolecular forces, external forces, and the pairwise intermolecular forces. So, now to relate these microscopic variables such as positions and momenta to simple thermodynamic averages, we are going to make use of a relationship called generalized equipartition theorem, which has two parts. The first part says that if I look at one component of the momentum of a particle I and then multiply that with the partial derivative of the Hamiltonian with respect to that particular part of the momentum, the product of that two should give you 1 kBt. Similarly, one component of the particle position and then multiply with the partial derivative of the Hamiltonian with respect to that component of position, that should give you 1 kBt. So, this is known as generalized equipartition theorem. We are going to skip the derivation of this theorem. We will just take this as a general result, and we try to use this equipartition theorem to relate temperature and momenta in the system. So, in order to do that, we first take this expression and later we will take this expression. So, now if you look at this, so I am just going to substitute for Hamiltonian from here. The Hamiltonian has two parts, as you can see here, kinetic energy and potential energy. So, when I substitute for H, I am substituting only the kinetic energy part because only that is a function of momenta. This potential energy is a function of only the coordinates. So, it will not survive in this partial derivative. So, that is omitted here. And now, if you look at within this partial derivative, I am going to write for one particular component, alpha component of an ith particle. Then you will see that in this particular summation only one term survives, which is the pi alpha squared by 2 mi. All the other components will not survive because this is a partial derivative with respect to pi alpha. So, I can write the relevant terms, and then now I can differentiate this. So, if I differentiate this expression with respect to dou pi alpha, I will get 2 times pi alpha, and the 2 and 2 will get cancelled, okay, and you get and then there is another pi alpha here. So, you get pi alpha squared divided by mi, and that should be equal to kBt. So, that is the consequence of the equipartition theorem is that for every component of the momentum, squared by mass should be equal to 1 kBt. So, now what we will do is we will sum over all the particles and all the components. So, I goes from 1 to n and alpha goes to x, y, z component, and then we sum over this particular pairs. So, then you will see on the right hand side you have 3n times kBt. For every one component there is kBt. Now, there are 3n number of such contributions. So, the total weight should be 3 times n times kBt. And now, what I can do, I can multiply by a factor of half on both sides, and then if you look at the left hand side, and this is nothing but the definition of kinetic energy. So, we are able to show then that the average kinetic energy is related to temperature of the system, and it also means that per degrees of freedom an average kinetic energy is about half a kBt. That means every particle will have a kinetic energy of 3/2 kBt. So, that is the average kinetic energy per particle. So, now we know an expression that relating the temperature to average kinetic energy of the system. So, now from the form relating the temperature and average kinetic energy, we can also define what is known as this instantaneous temperature by looking at instantaneous value of kinetic energy. Okay. We use the same expression from here and rewrite the temperature with a curled T as 2 times instantaneous kinetic energy by 3n kb. This expression are the same. Only difference is here we are talking about average kinetic energy and relate to the thermodynamic temperature, whereas in here we are taking instantaneous kinetic energy and relate correspondingly to a instantaneous temperature. And again you can substitute for the kinetic energy in terms of momenta, and you can also write it in a simpler notation. If you want to write this summation over the component form, you can simply write as the mod of pi squared by 2 mi, where you have to sum only from I is equal to 1 to n. All the componental form are written in a condensed form like this. And you would expect, as you know, that the average value of this instantaneous temperature should give you the thermodynamic temperature T over there. So, in all these cases, we took the number of degrees of freedom to be 3n, which is true for an atomistic system. On the other hand, if you have a molecular system where there are certain constraints in terms of bond angle and bond length, and the number of degrees of freedom may be less than 3n. So, suppose if you have nc number of constraints, then the total number of degrees of freedom will be 3n minus nc. So, that is what is reflected here. So, so we are able to see now that the temperature in the system can be related to the momentum or the kinetic energy. Next, we will look at pressure. How pressure is measured in a simulation using microscopic variables such as position and momentum. So, to do that, we take the second equipartition theorem, which is Qi alpha times dou h by dou Qi alpha should be equal to kBt. So, now first we will write for ith particle, which will have 3 components for alpha, x, y, z. Okay. So, that is this x component, y component and z component. When you sum them, you will get 3 times kBt because each one of them contributes to 1 kBt. Now, this 3 can be written in a vectorial form as Ri dot times dou h by dou Ri, where here this bold faced R vectorial form, whereas these ones are in component form. Okay. And this dou h by dou Ri is a is also written accordingly, and that is equal to 3 kBT. So now if you want, you can also write this particular expression as a gradient of the force, gradient of the potential energy, because we know that H is equal to K plus V, where this is a function of momentum and this is a function of coordinates. So this term will not survive in the partial derivative here, only this term remains. So then you are able to write the mean or average value of Ri dot del Ri V should be equal to 3 kBT. This is for ith particle. And this gradient basically means it's a derivative, partial derivative with respect to coordinate space of the potential energy. Kinetic term will not survive. So now we will extend this to n particle system by summing over I is equal to 1 to n, and then you will get on the right hand side 3 times n kBT. And then this derivative we will write as force, because the force, the vector force, is nothing but the negative of the gradient of the potential energy, as we know from mechanics. Okay. So that minus sign is taken to the other side, and then this del Riv is written in terms of total force. This suffix here, superscript T here, is the total force. And now within this particular angular bracket, we write the total force into a sum of external force and internal force. This external force is something you can think of the effect of the wall container in a real system, experimental system, whereas this internal force is because of intermolecular forces, which could be due to electrostatic interactions or van der Waals interactions, or bond angles, bond torsional potentials, bond potential, bond angle potentials. So all these intermolecular forces are encoded here, and all the boundary effects or external forces are in the external field. Now it can be shown, the proof I am skipping here is that if I look at only the external component, that should give you minus PV. This is something one can derive using kinetic theory of gases, whereas this part is something that comes from, as I said, from intermolecular forces. And what we are going to do is we are going to write this expression as to an internal virial. Okay, so this W here is known as internal virial, and we take this form and divide by 1 by 3, and that is what is defined as a virial. So now we are going to use these two definitions in here. Okay, so then you see that the first term is written as minus 3 PV, and the second term here is written as 3 times W, and that should be equal to minus 3 n kBT. And then if you divide by minus 3 across and then take the W to the other side, then you can show that PV is equal to n kBT plus average virial, internal virial. And if you like, you can also you can see that this first part is basically the ideal pressure part, and this is a contribution that comes via intermolecular forces. So what we can also do is we can define as an instantaneous pressure by and you take you divide by V on the right hand side. So you will see N by V is the rho, that is the average density, Kb times T. So I am replacing this average temperature to an instantaneous temperature because we are writing an expression for instantaneous pressure. And then you have the virial at that particular point of time divided by the volume. So the first part is nothing but the instantaneous ideal pressure, and the second part is going to be the excess pressure. So like we have done before, the total free energy can be written into ideal part plus excess part. We are able to show here the pressure can be also written into an ideal part and excess part. So ideal part comes only because of kinetic energy terms, and the excess pressure comes because of the intermolecular forces. So now the in the MD simulation, we are basically we will be trying to calculate the virial expression, and that can be used in the calculation of pressure like we said before. So this term can be analytically calculated because we know what's the density in the system, you know what's the temperature, whereas this part, the virial part, is related to the Ri dot Fi internal, Okay. So, this changes with the particle positions and relative positions, and this is something we measure in MD simulations. So, we will take the definition of internal virial. From now on, I am going to just skip this superscript internal. Everywhere here, F means it is basically F internal is basically F itself. Okay. We are not distinguishing between external anymore in this particular slide. So, now let us write the expression for the virial and then make use of certain properties such as pairwise interactions and Newton's third law, and write a simplified expression very similar to how we used to find pair interaction energies in MD simulations. So, first we start with the summation term I is equal to 1 to n Ri dot Fi, and this Fi is the force acting on ith particle because of all the other particle in the simulation. So, to calculate Fi, we do another sum j is equal to 1 to n Fij. We have to note that we should not repeat this index I and j, then it is like asking what is the force acting on particle by itself. So, that should not be included. So, that is why j is not equal to I condition should be imposed. So, now what we are going to do is we are going to just repeat this term twice and then you divide by 2. So, this is like writing x is equal to x plus x by 2. Why we do that? We will be clear in a moment. So, when I am able to rewrite the same term twice and then correcting for it, what I am also doing is I am also changing the index Ri to Rj, Fij to Fji, and these two terms are identical terms because even if I change this index of this summation, the values will not change. So, you can think of these two are basically the identical term. But the advantage of writing this way is that you can see that the force acting on ith particle due to j and the force acting on jth particle due to I, they are related by Newton's third law. Okay. So, the magnitude of the force is the same, only they are acting opposite to each other. Okay. So, that property is something we can use when we write in this particular form. So, I am going to write Fji as minus of Fij. So, now you can see this Fij is here and minus Fij is here. So, we can pull out Fij out of this and then we can write Fij dot Ri minus Rj, where Ri and Rj are the coordinates of particle I and j. So, then this Ri minus Rj can be written as the vector that separates the two particle I and j. So, it can be seen here if I have particle I here and particle j, Ri and Rj are the respective position vectors. So, Rij would be Ri minus Rj, which is a vector that goes from j to I. Okay, that is called the interparticle separation vector. So, what we are able to show is that the internal virial expression written in terms of particle position, individual particle positions and the total force acting on individual particle is now written in terms of pair interactions, pair interacting forces and pair separation vectors Rij and Rij. So, then we go to this expression and substitute this. So, we get internal virial is equal to 1 by 3 times sum over I to n, and then yes, there is one more thing I forgot to mention, that is if I look at this expression here, I goes to 1 to n, j also goes to I to n, except that j is not equal to I, and then we have a factor of half. So, now what I can do, I can actually eliminate this factor 1 by 2 by restricting the j to go from j greater than I to n only. Okay. So, that I do not have to do this. So, what I am trying to do here is I am doing double counting and then correcting for the double counting. So, instead I can just remove the double counting and change the index notation. One index will go from I is equal to 1 to n, whereas the other index will go from j greater than I to n, so that we do not do double counting. So, these two expressions are analogous, and this is a little expensive to do because you are unnecessarily adding the same forces twice and then correcting for it, whereas in this particular expression we basically avoid unnecessary calculations. So, that is why this index is now j is greater than I to n. So, now this expression we substitute in the internal virial and then you get 1 by 3 times sum I is equal to 1 to n, j greater than I to n, Rij dot Fij. So, now this Fij is nothing but the force between particle I and j, which is coming from a pair interactions. And now this force can be written in terms of the gradient of the potential energy V. This small v here is a pairwise interactions, which could be a square-wave interactions or Lennard-Jones interactions, etc., etc. So, now we are going to, so if you look at this, this gradient is a vector and Rij is also a vector, but the dot product of these two is going to be a scalar, okay, and this scalar we write as a pair virial, okay. So, with a small w. So, small w is a pair virial, which is nothing but r times dv by dr, which is a scalar, whereas this capital W is the internal virial, which is summed over all these pair I and j, okay. So, what we will be doing in our simulation is actually first, once you know the functional form of the potential V with respect to R, something like Lennard-Jones, we write like this. So, we know the functional form and then we take the derivative of V with respect to R, okay, and then you multiply that with R. So, that is an expression for pair virial, and that pair virial is actually calculated for all the pairs in the system, and that is what is going to give you the internal virial, which is capital W, which will be used for calculating the pressure. So, now we talked about temperature and pressure and how microscopic variables such as momentum and the position can be used to calculate average as well as instantaneous temperatures and pressures. So, another set of variables that are very much interested in MD simulation is calculation of free energies, because free energies are useful in finding out the phase behavior, stability, etc. So, now if you want to find the chemical potential, let us say mu as a function of density and temperature, we could say that I can do a grand canonical ensemble where we fix mu and V and T, and then in the simulation you find what is the density. Thereby you are able to get a relationship between mu and rho and T. Okay, so this is one way of doing calculating chemical potential. But the problem with this approach would be that in a grand canonical ensemble, as you might remember, the particles are getting added and deleted. Okay, but the particle number is fluctuating. So, when you are looking at a dense phase like a liquid and solid, inserting a particle and deleting a particle is very slow, and it is very difficult to do that, and sampling becomes very poor. So, in such a cases, this grand canonical ensemble is not very effective. Whereas, on the other hand, if you are looking at dilute gases, then grand canonical ensemble is the most simplest approach to calculate chemical potential. So, now let us see some other means of doing this free energy calculations. You may recall that for the NVT ensemble, the Helmholtz free energy is written in terms of the partition function, and the partition function itself can be written into two parts, ideal part and excess part. Okay. So, we split this up into two parts, and then we call them as a ideal free energy and excess free energy. We have seen this before. So, this ideal free energy can be analytically calculated because we know what is the partition function for ideal part, and from there we can get the free energy. The only thing that we do not know is this excess part. Okay. So, this excess part we do not know because this partition function is an integral over the configuration space in which the intermolecular forces will become important. So, to get an expression for this excess free energy, let us take what is the expression for an ensemble average of e to the power beta V. So, V here is the potential energy, beta here is inverse temperature times Kb, and let us find what is this average value is. So, in order to do this average, we have to recall an ensemble average of any property is written in terms of sum over or integral over the configuration space or the phase space, the property in those microstates times the weightage of those microstates via the probability function. So, we use this approach and find out what is the mean value of this exponential of beta V. So, we substitute that. So, we have the we substitute for rho, which is e power minus beta h by q nVt, and we want to basically find this value in the phase space. And what we can also do is, now you can actually do this momentum integral, write everything in terms of the ideal part, and this you can write in terms of ideal part and excess part, and you can see this ideal part will cancel, and then we are left with only the remaining terms, and if you look at what is remaining in the integral, you see that this is the function that we want to calculate, whereas the distribution function itself has the same value but the negative e power minus beta v, and they will cancel each other. Then you are basically only integrating dr, which will give you the volume power n, and the volume power n will get cancelled. So, the numerator will be just 1 and the denominator will be q nvt exponential. And this is interesting because if I know the average, the ensemble average of e power beta v, then I know what is q nvt excess. Then using this expression, I am able to get the excess free energy, and if you know the excess free energy, then I know the total free energy also. So, this looks like a one possible way to measure Helmholtz free energy in the system. However, you will see that, so that is what I have written here. So, once you substitute here, you will see this e power beta ax is nothing but the average of ensemble average of e power beta v. Now, the problem with this approach is that if you look at the distribution function of the canonical ensemble, we already noted that it is proportional to exponential of minus beta v. So, this distribution says that the microstate with the low energies are more likely to be visited than high energy states, whereas in this ensemble average, the energies, higher energy states are more valuable and more important. So, when you try to do this in a canonical ensemble, your estimate of this average will be limited by low energy states only, because this distribution does not allow a sampling of higher energy states, in which case these values are very important. So, on one hand, your trajectory is sampling low energy states, whereas the average that you want to calculate is weighted more at higher energy state than at lower energy state. So, this will lead to a poor sampling problem. You will always underestimate the value of this ensemble average, thereby you will be underestimating your free energies also. So, this will lead to poor sampling and incorrect excess free energy values. So, we do not take this as a possible approach. So, what other approaches we can do which is reliable? So, to do that, we go to classical thermodynamic relations, which relates the energy in the system to a Helmholtz free energy via this expression. You can easily derive this. And now, let us say if you want to look at a constant volume and number of particles, you can write that the d times beta a is equal to E beta. So, this is coming right from here. So, now let us integrate this in between two temperatures beta 1 and beta 2, inverse temperature beta 1 and beta 2. Okay. On the left hand side, you will have beta a measured at beta 2 and beta a measured at beta 1. On the right hand side, you have to basically integrate from beta 1 to beta 2 E d beta. So, now this d beta you can actually write in terms of dt from the relationship that beta is equal to 1 by kBt. So, when you take d beta, you will see minus 1 kb t square dt. So, this can be written in terms of dt on the left hand side, and you can also divide the entire expression with n, so that we can talk about energy per particle, and beta is substituted as 1 by kBt here and here. So, we are talking about difference in the Helmholtz free energy per particle between two states, two temperatures T1 and T2, and that should be equal to integral from T1 to T2 E by n kBt square dt. So, this can be easily obtained from our MD simulation, because what you see here E is nothing but is the average energy that you can obtain from your NVT simulations. So, the way you would use this expression is that you basically do NVT simulations at a different temperatures. So, multiple NVT simulations at a different temperature. In each of those simulations, you get the average energy. So, basically you can plot the temperature versus the average energy in each case. Okay, and you are going to just take these points and then use it here and then integrate between the limit T1 to T2, and that should give you the difference in the free energy. So, this is known as thermodynamic integration. So, to get one free energy value at a particular temperature, you need two things. One is a reference state to start from for which the free energy should be known, and second, we need a set of NVT simulations with the different temperatures, and then get enough number of average energies across those temperature ranges, and then do numerical integration of this particular calculations. So, this is one way to find the Gibbs Helmholtz free energy at a given temperature and volume. Now, you can also do the same thing with pressure, in the sense you take this thermodynamic relation. P is related to negative of dou A by dou V at constant, yes, at constant temperature and number. Okay. So, we are still talking about NVT ensemble, same as here. So, here we integrate this between two states 1 and 2, and the volume goes from V1 to V2 P dV, and again we can write per particle per kBT, and then right hand side also becomes P by kBT. So, now to do this, all you need to do is, like here different temperature and you measure the energy. Here you will be doing different volumes and then measure the average pressure in each of those NVT simulations. So, you are going to do NVT simulations with the different volumes and then get the pressure values and use those pressure values to do this integral. So, it becomes possible then to find the free energy difference between state 1 and 2 using a series of NVT simulations with the different volumes and then measuring the pressures in those volumes and then using this integral numerically. So, now let us say you are interested in measuring chemical potential. So, then we look at the definition of chemical potential either using Helmholtz free energy or Gibbs free energy. And then if you look at a very large system size n, this mu can be written in terms of difference in A and difference in n. So, this delta A is nothing but the free energy of n plus 1 particle system minus free energy of the n particle system, and delta n is nothing but n plus 1 minus n. Now, we are going to replace this with the corresponding partition function. So, and similarly this also, and now we can write, so in the denominator will be just 1, and then this can be written as ln of q n plus 1 by q n. And so, now what we can do is, we know the expression for q n, especially if you are talking about ideal and excess part, we know what is the expression for. We can substitute it here and then you can write into two parts, an ideal part and an excess part. And then the ideal part, the only difference is when you write this q for n plus 1 system, wherever you have n, you should put n plus 1. So, you can see this term becomes v power n plus 1 factorial lambda 3 times n plus 1, whereas this q n I d is just the inverse of this here because it is in the denominator. So, that is simple, and then you can see there are many terms which are cancelled, and then you will have the final term here which we call as an ideal part of the chemical potential. Similarly, if you look at the excess part, so you are going to substitute wherever n is, you are going to substitute n plus 1 for the numerator, and then you get 1 by v n plus 1 integral over configurational space with the n plus 1 particle, and then this is the potential energy for n plus 1 particle system, and in the denominator you will have the same expression like this for n particle system. So, and then so we will keep, so you see this v power n get cancels, you have 1 by v here. So, this part we call it as excess chemical potential. So, now if you look at the expression for excess chemical potential, we see that it is something possible to calculate in a MD simulations or Monte Carlo simulations, and that is because if you look at here, this is the potential energy for a n plus 1 particle system, which can be written as sum of the potential energy of n particle system plus some delta V between the two systems of n plus 1 and n. And then if you look at this, you see this is nothing but an ensemble average of exponential of minus beta delta V. So, in other words, the excess chemical potential can be written as minus kBT ln of an ensemble average of this property e power minus beta delta V. So, this is something one can do it in a simulation by adding a, so what you do is you take a simulation with the n particle and then you try to add a ghost particle, see what is the difference in the potential energy, and then you remove the particle, and then you continue this many times, and then you will get an ensemble average of e power minus beta delta V, and that is nothing but your excess chemical potential. So, this can be done easily in NVT because the volume here is constant. If you want to do it in NPT, you can use the same expression like before, but only correction we have to do is this volume is a fluctuating quantity. So, we are going to put this 1 by V as a ensemble average, and then you are going to have another V in the another ensemble average. So, you are going to look at two such quantities, average V as well as average of volume times exponential of minus beta delta V. So, we have to remember that when we add this one particle and make the particle system into n plus 1, we are not really adding a particle, we are only testing if I put the particle in the system, how much energy change will happen. We are just interested only to find out what is the change in energy, and then we take the particle away. So, it is like a ghost particle, it just gets inserted only to find what is the change in the energy by inserting a particle. So, you can also do the same analysis by going from n to n minus 1 system. That means, you have a system of n particle, try to remove a particle and see how much energy change has happened, and then you put it back. Okay. So, either way it is possible, either you can add a particle and test, or you can remove a particle and test what is the change in energy, and do an ensemble average of that change in energy. That should give you the chemical potential excess, whereas the ideal part already we know from analytically. So, with that, I hope we looked at some simple thermodynamic averages that could be related with microscopic data such as momentum and particle positions. We showed explicit expressions for using kinetic energy and potential energy, and then using it for temperature, average temperature and instantaneous temperature, as well as average pressure and instantaneous pressure, internal virial and parivirial. We also showed some examples of thermodynamic integration, which allows you to calculate change in the free energy between two temperatures or two different volumes. And finally, we also looked at this particle insertion method to measure excess chemical potential.